Okay, let's go. Hello everyone, my name is V, and today I will presenting on the topic of electric load forecasting. And our group includes Nguyễn Đình Thái, Ông Lương Tiến Huy, and myself, Nguyễn Đức Giao Huy. And our topic focus on applying statistical and machine learning model to perform short-term electricity forecasting, especially on the next uh, 24 hours and 7 days. Now we will begin on presentation. Uh, in my presentation, we have four parts. The first is introduced by an data analysis. Second is literature reviews on each algorithms. And third is apply ARIMA and Hall-Winter in forecasting. And and the last is the regression algorithm results. We next to the first part, introduction and data analysis. This study applied the ARIMA, Hall-Winter, and machine learning regression model to forecast short-term electric demand using half-hourly data by combining time series analysis with regression techniques and tunings via cross validation. And the approach improves accuracy and supports effective energy plan. The data is ideal for the data is ideal for studying demand patterns, seasonal trends, and the impact of temperature and holidays on demand, make it suitable for time series forecasting and related analysis. And there are options for both demand and temperature. The average demand you can see in the figure 2. And the line chart illustrates the variation in electricity demand recorded over the entire observation period. And the demand fluctuate significantly with value ranging as approximately three, between 300 and 900 units, noticeable peak and throughout seconds. And, and demand variation throughout the week. And demand is general highs from Monday to Fridays, with slightly dip on Sunday and Saturdays. This suggests a reduced electricity during weekend or rest day. And higher demand is observed during the early month and mid-year, while lower consumption appear towards the end of year. This variation may be linked to seasonal factors such as temperature and change or holidays. And demand values are approximate, normally distributed but with a slight rise skew, indicating a long tail toward higher demand level. Most demand values fall between 300 and 600, 3, 3,000 and 6,000 units, with two noticeable peak around uh, 4,500 and 5,000 units, suggesting common demand range during the observation period. This distribution insight is crucial for understanding typical consumption pattern and i- identifying outlier. And this picture shows the decompositions of the electric demand time series into fundamental components, chain, seasonal, and cyclic, and the relevant the chain components show the second panels. capture the long-term progression of demand, indicating the period of gradual increase and decrease over the observed time. The seasonal reflect the consistent, repetitive pattern occurring daily, highlighting the interesting periodic behavior of electric consumption. And finally, the residual components represents the irregular variation or noise remain after accounting for change and seasonal effect. Uh, that's the right picture. A scatter plot, illustrating the relationship between the city and temperature, and by the calculated Pearson correlation coefficient between demand and temperature is indicating a weak positive linear relationship. And and you can see in the left picture the demand during the regular days tend to be higher with a median value above that of holidays. And the test static obtained was with an associated p-values you can see in the pictures, and and the p-value is significantly less than 0. We reject the non-hypothesis of the presence or of a unit root, indicating that the time series is stationary. And these ACF and PACF of demand. And for the second part, ông Lương Tiến Huy will present.
We move on to the second part is literature reviews, and we have four parts here: the ARIMA models, or winter models, random forest, and the last one is HG boost. Uh, the first one is about the whole winters model. Uh, the whole winter method, also known as triple exponential smoothing, is a statistical technique designed for time series forecasting, particularly effective for data exhibiting both trends and seasonality. Originating from the work of Hose 1957 and further developed by Winters in 1960s. It extends the simple exponential smoothing and holds double exponential smoothing by incorporating a seasonal component. This make this make it a robust tool for capturing complex patterns in time series data, such as monthly sale figures. There about the characteristic of Hovito, we have two variations of the method, each suited to different data behaviors. Uh, the first one is addictive. Roughly constant over time. Here the seasonal component is expressed in absolute terms, and the sum of seasonal effects within the circle is approximately zero. This is ideal for data where seasonal impacts do not scale with the overall level, such as consistent monthly temperature variations. The second part is multiplicative whole winters. We use when the seasonal variations are proportional to the level of series. The seasonal component is in relative terms with the sum within a circle approximately equal to the number of season M&M. This is suitable for data like sales where seasonal effects grows as the overall sales volume increase. And the method relies on three smoothing parameters. The alpha, this controls smoothing of level ranging from 0 to 1, where higher values give more weight to recent observations. The beta manage the trend smoothing also between 0 and 1, affecting how quickly the trends adjust to new data. The gamma thus handles seasonality smoothing with values between 0 and 1, influencing the seasonal component's responsiveness. These parameters are typically optimized to minimize forecast errors, and the method's equations involve recurrence relations requiring initial values for level, trends, and seasonal components to start the forecasting process. The method is not for ease of implementations, supported by tools like Python's Start Model, R's Forecast package, and even Excel, making it accessible for practitioners without advanced statistical software. However, it is sensitive to outliers as sudden change can disproportionately affect the smoothing parameters. And we move to the second is ARIMA models. The ARIMA is stand for the autoregressive integrative moving average. Is a cornerstone of time series forecasting, renowned for its ability to model univariate time series with autocorrelations trends, and through its seasonal attentions, its ARIMA periodicities. The ARIMA have three core components: the autoregressions, the integrations, and moving average. The first one is the RA is autoregressions. It is the models the current value as a linear combinations of p previous values. For instance, an AR model expresses the current observations as a function of immediately preceding value. The integrations thus employ different things to transform a non-stationary series into stationary one, with the indicating the number of different things operations. For example, D equal 1 involves subtracting consecutive observations to remove linear trends, and the moving average, that's MA, represents the current values as a function of quick-path forecast errors, capturing residual dependencies. And we have the seasonal ARIMA, that is for time series with periodic patterns. This one is X10 ARIMA, where the PDQ are seasonal AR different things and MA orders, and M is a seasonal period. This enables modeling of seasonal effects such as holiday sales spikes and the stationary requirement. The ARIMA requires the time series to be stationary. Constant means the variance over time or made stationary through different things or transformations. Stationarity is typically verified using statistical tests like the augmented Dickey Fuller, that is ADF test, and the parameter estimations for SARIMA is ACF or PACF as stationary test to select D and automate algorithms such as AutoRima in R's forecast package or AutoRima in Python PMDRIMA. And we move to the XGBoost. XGBoost is an open source machine learning library specifically designed to tackle regression and classification problems. Developed by Tianqi Chen, it was first introduced in 2014 and has since gained immense popularity due to its exceptional performance in both accuracy and speed. XGBoost is gradient boosting framework, which means it builds predictive models by combining the predictions of multiple weaker models, typically decision trees. The XGBoost have the hyperparametric tuning, thus provides several important parameters to optimize model performance, categorized into three main groups: general parameters, booster parameters, and learning task parameters. About the general parameter is have the booster, verbosity, and end thread. About the booster parameter is have the ETR, that is learning rate, and the max diff, and the mean child weight. Of learning task parameters, that is objective, evo metrics. The last one about the early stopping, that is have the early stopping routes. The last algorithm we have today is the random forest. Random forest is supervised learning algorithms that can solve both regression and classification problems. Random in random forest is referred to randomness, and forest refers to the collections of trees. Therefore, in the random forest algorithm, we build multiple decision trees using the decision trees algorithms. However, each decision tree is different. The prediction results are then aggregated from the decision trees. During the training phase, we build many decision trees, and this tree can be different. And how to build the random forest algorithms. We assume that our data set has n data points, and each data point has d attributes. And to build each decision trees, we do the following step. The first one, we randomly sample n data points from the dataset using the bootstrapping technique, also known as random sampling with replacement. This means that when we sample a data point, we don't remove it from the original dataset, but keep it in and continue sampling until we have n data points. The second step is After sampling n data points, we randomly select k attributes where k is smaller than n. Now we have a new dataset with n data points, and each data point had k attributes. The last one is use the decision trees algorithm to build a decision tree which with the data set from step 2. Since the process of building each decision tree has a random element, the resulting decision trees in the random forest algorithm may differ from each other. The random forest algorithm consists of many decision trees, each built using the decision tree algorithm on different datasets and using different sets of attributes. Then, the prediction result of the random forest algorithms is accurate from the decision trees. When using the random forest algorithm, we often pay attention to parameters such as the number of decision trees to build the number of attributes to use for building the trees. And the next part is about the ARIMA and whole winter resource by tiding.
Okay, we have our task is forecast thing for 24 hours and 7 days. About the data sets, we have the data set which includes time, demand, and temperatures. But in this process, we use just time and demand for forecasting. First, we use the code block different tiers to find D in ARIMA model. So look at the graph. You can see there's no clear trend over time, so that the input data series is already stationary. So no need to check difference. We will apply it to the model, including training days, to predict the next day. We apply PDQ as default, P equal to 2, E equal to 0, and Q equal to 1. Then we forecast validation to check the model forecast performance on time series. Performance on time series through a sliding window. Window equal to 96 equal to 4 days. Training step 1 equal to 1 hour sliding, and horizons equal to 22. And we check performance by relative error. Relative errors equal to forecast value minus to actual values divided by actual value and plus 100%. In that, RE is relative error for each point. Forecast value is prediction value for each point or positions. And actual value is the original value of each position. So we have 3 graphs of positions, and we can see that in the position 1, they have the good performance. And here is the own results of 24 positions. This is the value of demand forecast for each position of 24. And we can see that the position 1 to 3 is good have a good performance. Next, about the 7 days forecasting, we merge data into 1 day per 1 data point. so that we have the graph. The first graph is about result for position 1. And the second graph is the demand and forecast for position 4. Here is relative error of 7 position point. It's about 5.8% to 15%. Next is the process of whole winter. Similar to ARIMA, we have 3 main setup for whole winter: the alpha, the beta, and gamma. All three coefficients range from 1 to 0. High value provide fast response, but susceptible to noise. Low values provide smooth but slow response. Choosing the right alpha, beta, and gamma helps the models balance between forecast accuracy and stability. In practice, these coefficients are often automatically optimized using grid search or machine learning algorithms to achieve the lowest error. So in this case, we using alpha, beta, and gamma as default, as the setup default in AI Studio. So we have the results. In the left is the result of position 1, and the second is the forecast for season 17. Next is result for 24 positions. It's rate from 7.22 to about more than 50%. I think it's quite not a good performance, because we set up alpha, beta, and gamma as default. So in the future, we want to use more method to find good setup, and so that we can find the good results. Next is about the 7 days forecasting. First is the forecast position 1, forecasting demand, and forecast position 3 in the right graph. And here is the result of 7-day forecasting for winter. It's about 8.8% to 17%. No, to more than 20%. And the accuracy for whole winter in 1 day per data point. The ARIMA model was established with optimal parameter P equal to 2, D equal to 0, and Q equal to 1. After performing the stationary test, the whole winter model is multiplicative smoothing method to fit data with seasonal factors that vary in amplitude, with the parameters alpha equal to 0.5, beta equal to 0.1, and gamma is equal to 0.5. The model gives forecast result with the relative error for 24 hours, reaching 38.7% to more than 50%. And the relative error for 7 days being 21.3% to more than 35%, which are significantly poor than ARIMA. The chart show that the forecast line not closely follow the trend and cycle of the actual data. However, because Howinter is a linear model, its ability to respond to sudden fluctuation still limited. However, with current data, the Howinter model has so poor performance to ARIMA in terms of accuracy. So now we move on to part 4, the regression algorithm results. And I want Nguyễn Đức Gia Huy help me to present.
To the regression algorithm results. First, we're using the feature engineering to handle time-space features, hour, weekdays, and month to go transform using the scene code function to preserve continuities. And actually, lag features like demand lag 1, demand lag 24, demand lag 48 were created to capture short-term and daily patterns. Missing values from lagging we drove. The final dataset includes the silicon features, external variables, or exogenous variables, temperatures and holidays, and demand with demands as the target variable. Uh, you can see in the left pictures, we change the hours into our scene and our cost. Weekdays is transformed to weekday corrected from 0 to 6, and weekday of scene transformed to scene and cost, and we select some lag like 1, 2, 3, 23, 24, 25, 48 for lag, and in the right picture, it is features apply for regression. And we're using the XGBoost Bayesian model was trained for time series forecasting using the mean absolute errors as the evolution metric. And we use the research to hyperparameters by using the an estimator max depth learning rate. Recursive forecasting was used for validation. The both best models was selected based on the lowest MAE, and we apply the best model to the test set. And the best hyperparameter identified through the research follow the full sample by trees is equal 0, equal 1, learning rate equal 0.01, max step equal 5, and estimator equal 1000. And this setting will found to zero the optimal model performance during the tuning process. And after converting the initial models on the test sets, the absolute error was calculated by subtracting the predict values from the true test values. And this error was then stored in the data frame. The app results, the app results the app results XGBoost, which include actual values, predicted values, and the corresponding absolute errors. And you can see here is a plot. The plot was generated to visualize, compare the actual demand and the predicted demand and the absolute error. And in the right picture, you can see in the right picture, it is the this plot the demand in predict for 24 hours. Next 24 hours, and this is the load forecasting for 1 week. And the XGBoost model demonstrates the relative boost performance in the forecasting electrical load demand as reflected in the test results. The above the absolute error values indicating that the models achieve high accuracy at many time points with several error below 10 megawatt. However, a large derivation exceeding 500 megawatt in certain case, highlighting the limitation in capture sudden load fluctuation. In the short-term forecast visualization, the model successfully check the general trend of the actual loads, but exhibit a time lag during the sub transition. And nonetheless, the model output tend to be over smooth, reducing sensitive to group peak or drop in demand. And this finding suggests that why XGBoost is suitable for baseline load forecasting in relatively stable condition. Its performance can be further enhanced by incorporating features related to temporal dynamics, cylinder effect, or exogenous variables such as weather data. And we need to the linear other regression model support factor regression. And the hyperparameter tunings for the support factor regression this model was carried out using the research approach for multiple combination of key parameters. It sees the regularization parameter with possible values of 100, 500, and kernels, what type of kernel used in the model set to the radio basis function, IBF kernel. In gamma, we use the scale 0.01, 0.1, and 1. And epsilon, the epsilon driver used in the test was 0.1, 0.01, and 0.005. And you can see um, and you can see in the pictures, the performance of SVR models on the test sets appear to be significantly limited in the context of electrical forecasting. As observed in the chart, the true loss, blue light, exhibit the fluctuation and the clear spherical patterns, which are typically of real-world electricity demand data. However, the SVR remain almost constant across the entire time range, centered around the average demand level. And this indicates that the model failed to capture both the temporal dynamics and the periodic nature of the load series. The inability to flow peak and through suggests that SVR as implemented here lack the necessary adaptabilities for high variance time series. The predictions error is consistently high, particularly during peak load hour and low demand periods due to the model's static output. Such behavior point to poor generalized capacities for SVR in the use case, possibly stemming from inadequate feature engineerings or suboptimal hyperparameter tunings. And we next to the The last algorithm, the random forest. And in the random forest, we use to tune the random forest, we model by testing the combination of key parameter, the n estimator, the mark depth, the mean sample split, the mean sample lift, and random state. The goal was to find the best configuration for accurate, robust forecasting. The top performance combining was selected for final training. And with the combination of mark depth equal 10, mean sample length equal 1, and mean sample split equal 2, without in the validation mean absolute errors of thing is as the mass model at that point, subsequent child with different values for the hyperparameter reveal further improvement. With the combination of mark uh, and this configuration ultimately led to the identification of the best performing model with the lowest MAE, setting the stage that the final evolution of the model performance. And in the lectures, we use some of parameter to find out the best models. And the random forest was exhibits the moderate to good performance in the forecasting electric load on the test sets, and based on the absolute error tables, the model applied the reasonable accuracy at the several points with error lows as 2.6 megawatt, 2.6 megawatt, and most prediction remain within 50 to 200 megawatt error range. However, there are instances of overestimation or underestimation, such as error existing 600 megawatt and even 1,600 megawatt at certain points, indicating instability with predict during the period of sharp demand fluctuations. And for overall for random, and this picture shows the load forecast for 1 day and the load forecast for 1 week. And overall, random forest perform acceptably for baseline forecasting and capture cyclical behavior better than the modelized SVR. However, it's performing diminished under high variance conditions, suggesting that further engines such as incorporating temporal features or using hybrid model would be necessary to improve the robustness and the prediction accuracies in more dynamic real-world load forecasting scenarios. And go next to the conclusions. Uh, you can this table shows the AME, IMSE, and attributes of each algorithm we use. XGBoost with the lowest AME, both lowest AME and IMSE, and R2 next to the random forest, and SVR with the back. And in this context, in this study, address short-term electricity demands forecasting after pre-processing and time series analysis, ICF, time model will compare. I remind how winter It's good for chance and seasonalities, but struggle with volatilities and nonlinearities. As we are captured on nonlinear pattern via feature engineerings, improve accuracy with extensive tuning, runs the forest strong in stable condition over smooth sudden change. Physical boost is a better overall performance, balancing short-term dynamics, seasonalities, and efficiencies. And conclusions, the machine learning models, especially XGBoost, outperform classical method. Further work may explore the deep learning and integrate external factor. And it's all about my presentation. Thank you for listening. It's time for questions.
Uh,
Uh,
I have the first question is, which engineered features were the most important for each model?
The report explains that lag and cyclical features were created to have the model learn, noting that the daemon lag 24 is a very strong feature. But however, the document does not include formal feature importance analyzed to quantitative rank. That's my we will fix this later.
And I have
uh,
another question is, why did Arima outperform than whole winter?
uh,
Hmm.
I think Arima performed better because the whole winter model being linear and struggle with the dataset high volatilities and sudden fluctuations. It forecast did not close follow the actual data chain, and the result is significant higher 24-hour relative errors for her winters compared to Arima. Can you
However, in whole winter, we don't try to use good alpha, beta, and gamma. We just set up as default so that it's not have a good performance compared to Arima. Another question.
I have a question. What do you think uh, you can do to improve XGB model?
Well,
I
the
think
XGB model, I will invite Zawi to answer. Mm,
I think
okay, Zawi, answer.
to improve the EcoBoost model and then its forecasting performance, I will do some method. The first is feature enrichment. I can add exogenous variable like monitor weather data, electricity pricing information, and other. And also I can add time-related features like feature related to temporal dynamics and cylinder effect. And I also using the more advanced model architectures like LSTM, long short-term memories, and temporal convolution network (PCN). These models are often better at capturing complex dependence in time series data.
Okay, thank you. I have another question. Task requires forecast 1 day and 1 week, but in ARIMA model, I can get it. What do you forecast 1 day and 1 week?
I'm not clear your question. Can you explain?
In regression task, you plot 24 hour and actual. It's in slide 54, and I don't see it in ARIMA model.
Which slide do you mean?
In slide
Here.
54,
Here is
you can
forecast
see.
for ARIMA. Here's forecast for ARIMA, and here is forecast ARIMA in 1 week, and here is about 1 day. Clear?
Why I don't see the plot compare about your forecast and actual, like random forest model.
Graph. And the graph in ARIMA here. There's about there's so much graph, so I just put 3 model graph in here. And about XGBoost.
Yeah, yes, sorry, but can you open ARIMA?
Open ARIMA again.
Yeah.
Here.
Yeah. Next slide. Slide 32.
32.
Yeah. Yeah. I don't catch that. What do you do in this slide? Can you explain? What is okay?
In the figure 15, we can see the forecast position in position 1 and the demand, the original demand in position 1. Clear? So in the next to another figure, we will forecast. We have to forecast position and demand in position 15 and position 22 here. The green is the forecast, and the blue one is original demand. And you can see for the position 1 to another positions, we have low and low performance.
what day you forecast? You show me the table in slide 33, but I don't know what day you forecast. It's I don't get it. What day you forecast in table 33?
Here. It's about April.
It's about the forecast for T plus 1 and T plus 2 and T plus 24. And each of it has the euro. You can see in the table of slide 33. And for the T plus 1, the relative error is so small, and for the 24 T plus 24, the relative error is very high. And yeah, it's all.
Oh, okay.
About the table.
So why T plus 15 higher than T plus 22?
I think in T plus 1 to T plus 3, we have the data sets which has the chance so clearly. And for the T plus 4 to T plus 24, the data sets before is not clearly make a chance to predict